Good afternoon. Thank you for your time. I think I can use this. So this work is in collaboration with Professor Torellas at UIUC. So just to see this is what you saw several times today. We are way off the power budget for exascale machines. If even for Limpact, let's say 26 times less energy efficient than exascale. So we need different designs and new approaches that would save a lot of power, not just a little. And I'm proposing something that I think can save quite some power. So caches consume a large fraction of processor's power. The Power 7 paper says 40% after a lot of optimizations. It's typical in processors to consume like 50% of the chip's power in caches. And these caches are getting larger and larger every day, driven by the market. Like some high-end Xeons have like 30 megabytes of cache in their last level cache. Power 8 has 96 megabytes of L3 cache. This is a fixed design, so not all applications need it. Some extreme case, if you have like pointer chasing through big data, you don't have much locality, you are not using the cache. That 50%, 40% is just waste. Just to look at a specific example, we have NAMD developers here. So let's look at NAMD on blue waters to be very concrete. For the HIV simulations for a recent discovery that Sanjay explained this morning, they had 64 million atoms. The state of each atom that's being checkpointed is just 48 bytes. But with all the transient data, multicast of forces, all of that, let's say we have 400 bytes per atom, which is 25.6 gigabytes across the whole machine. For the simulations in the documents, I found that for a lot of them, they used 4,000 Cray nodes. Some NAMD developers can confirm. So the whole configuration has 256 gigabytes of cache. So 90% of the capacity is not used during the simulation. Just a disclaimer, this is not NAMD's problem. There is nothing wrong with NAMD. Actually, it should be even less usage in strong scaling, as Sanjay was pointing, like 5 atoms per core. So this is a problem of the machines. Each simulation took like takes like 16 days of wall clock time. So this is a huge waste of power in current supercomputers. So this is a recognized problem. There had been a lot of work which try to turn off ways of set associative caches. If you turn ways of set associative caches, not much is changed. So this is the easiest way to do that. But there are two main issues. How would you predict the future of the application in the hardware? How much should you profile in the hardware? You have profiling overheads. And even if you knew what's going to happen, what is the best configuration to use? So we can solve both of the issues on HPC systems, just on HPC systems for now, but it could be extended. So HPC systems are built using commodity processors, which are not designed for HPC most of the time. IBM machines are tweaked a little bit, but like Cray, just off-the-shelf processors. However, so something that we exploit is that provisioning is very different than non-HPC machines. We don't have multi-programming, time-sharing, co-location. We have large, long jobs, high predictability. So we can exploit that for HPC. It's not like Google's data center, virtual machines moving around all the time, very short search jobs. We have long simulations. 16 days was a typical thing. So another thing that we exploit is the inherent properties of common HPC applications. So for particle, I call this class particle interactions. We have NAMDs in this class, or I'm using Mantivo Mini App Suite to represent common applications. MiniMD and CoMD are in this class. They have force computation of some limited number of entities. So they have a small domain and high temporal locality, because these entities are interacting with each other in a small domain. There are a lot of repeated accesses. Another big class is Stencil. In Mantivo suite, if you're familiar, Cloverleaf and Minighost. You have a lot of grid points in a domain, and you update them through iterations, update all the grid points. So you have a very large domain and low temporal locality, because by the time you get back to the start of the domain, it's already out of the cache. There is some locality, but it's limited. So the next class is sparse linear algebra. In Mantivo suite, HPC CG, Mini-FE, and Mini-XIC are in this class. So these examples I have are like almost all of the Mantivo suite. This is like these three classes encompass all of them. So this linear algebra is very similar to Stencil for more real applications. You have update of some grid points, like the matrices has come from some domain. You're updating through matrix vector multiplication. So it has low temporal locality, often large domain. So we are going to exploit these these patterns. Just to see a concrete example, this is the 5-point stencil. This point over here is updated with the neighboring points. And the next iteration is going to update this point, the neighboring point. So from the hardware's point of view, 3 range of addresses are being streamed. If you block it, it's going to be one range of address. It's going to be much better. But still, you are having a streaming pattern. This is known. There had been a lot of work on streaming. But I'm going to show a better way of streaming here. So what we propose is that since HPC applications are iterative, and there is a lot of persistence, the same pattern repeats, the runtime system can predict the future much more easily than the hardware or compiler or anything else. We can predict the future. I'm going to go to a little bit of more details about how. Also, we have a single program, multiple data. So different processors typically do the same thing. Divide the domain, they are doing the same thing. So we can try different configurations in parallel, exhaustively. If you have like a cache hierarchy, the number of configurations is like 70, 80 maybe, but you might have thousands of nodes. So the two problems of cache reconfiguration can be solved easily. Prediction of the future, finding the best configuration. And the runtime system can monitor if the application changed phases, this could be done again. So what does the runtime system see? It sees it can track sequential execution blocks, which we define as the computation between communication calls. We might have MPI received and MPI all reduced. These SCBs are identified by the communication call, their arguments, their duration, some performance counters, but even the duration and communication calls are enough. These are getting repeated in every iteration. If you have a stencil, receive, send, then compute again and again. Maybe some are reduced in between. So this is the reconfiguration unit. But to handle more complicated cases, so I said we can predict the future. So let's see how a more complicated application looks like. So this is MILC, well-known application used for acceptance test of blue waters. It has a hierarchical structure. So this graph shows different processors. These are stacked, but as I claimed, they look very similar. They do the same things, and the same things repeat on each processor. So we have one overall iteration. I think it does some near neighbor kind of thing, then some solver, CG solver in each overall iteration. And we have some sub-iterations in this overall iteration. So we have a hierarchical iteration structure. So what we need is to identify this iteration structure and be able to predict. I want to know what SEB is going to come next to reconfigure the cache to match that SEB. In the general case, it's difficult. It's not as simple as some benchmarks. What we are going to use is formal language theory because we have a pattern recognition problem. We define each SEB as a symbol of an alphabet sigma. An iterative structure is a regular language by this mapping, theoretical mapping. And it can be proved by construction easily because we can construct a regular expression from that structure, step by step, infinite number of steps. So each execution is a word of this language. We might have different number of iterations. So this is a word of the language. So we have a pattern recognition problem here. We have a regular language. We want to learn it. In profiling, the runtime system sees a stream of SEBs. Hey, MPI receive reduce one SEB, then the next SEB, and so on. So it needs to identify the pattern, the iterative structure. This could be mapped to a classical pattern recognition problem, which is called learning a regular language from text. You have some text of symbols. You want to learn the regular language. So in this case, we want to build a DFA for this language to be used for prediction. The simplest solution is to use a prefix tree acceptor. This kind of DFA has a state for every prefix of the profile stage. So this is an example here. If I have ABC, I have profile ABC. I have one state for A, one state for AB, one state for ABC. There's a lot of work in this domain to reduce this number of states, but we don't need it for our purpose because this number is already small for our purpose. So this is the way the runtime could build a DFA in the general case and predict the future of the application. Just to see how far it could go for some Mantivo mini apps, we did some simulations of different cache configurations to see how much we could save with something like that. So we use Mantivo mini app suite. We assume the MPI OpenMP just to be the same across the applications, and this OpenMP actually makes it a bit more complicated for us. We identify unique SEBs, and we use CESC cycle accuracy simulator to simulate different configurations for each SEB. There is no machine as of today that could let software reconfigure the caches. There is the MIT Angstrom processor in the prototyping stage. I don't think it's functional yet, but I would be interested in using it. We model the cache power energy using Cacti, which is a standard tool. So let's see what configurations the runtime would choose for each application. The best configuration depends on the application type and input size. So for these applications, I've listed a table. L1D cache, L1I cache, L2 and L3. Number of ways that, total number of ways, the number of ways that are kept on in this configuration. So we see that a lot of the ways could be turned off. There is a lot of analysis why L1 caches don't need too much size for SEB or these applications, how much of the L3 cache we need, and so on. But in the interest of time, I'm not going to go through all of them. But as you can see, the configurations are diverse, depending on the application and the input size. Sure. So 1/4 means the configuration has only one way out of 4 ways of the cache on. So 1/4 of the cache is on for L1D cache.
What you're putting in the table is the optimal configuration. You evaluated keeping 1 out of 4 on, 2 out of 4 on, 3 out of 4 on, 4 out of 4 on, or maybe not 3. But, and out of those, the 1 out of 4 turned out to be optimal.
Yeah.
That is, in what sense optimal?
We tried all the configurations exhaustively, and this is the best configuration of this machine.
Best configuration for saving energy, but I suppose it's always 1 out of 8 if for 1 out of anything for best for that. It's just that without having much impact on performance, right?
Yeah.
So that's how did you judge that?
So you could have you could put different thresholds. This is without too much performance penalty.
What is 5%? 10%?
This is no. This is, I think the cap is 1%,
okay,
something like that, for this result. So this is the best without too much performance penalty, the best configuration. Actually, if you just, I think the total number of configurations is just 70 or 80 if you can turn on in powers of 2, 1 way, or 2 ways, or 4 ways, or 8 ways. There aren't too many configurations with these restrictions. Go ahead.
Why? I mean, the total number of ways. Why is that 4?
What is that?
The total number of ways for L1D. Why is that 4? Is there some reason why it's 4? I mean,
there are 4 ways in the processor. So the L1D cache. So for the it has 4 different. A set associative cache has 4 ways. So the same address could go to 4 different ways. This is just the design of the processor. So this number could be anything depending on what Intel or other vendors would provide. These numbers are determined through benchmarks that are not really HPC sometimes. So looking at the power savings we could have with a little performance penalty, like 2% on average, with some penalty cap of 4 or 5%, we could save 67% of the cache energy on average across the board, like for the Mantivo mini app suite, which is very significant. If you assume 40% for the processor's energy, it's like 20% of the whole processor could be saved with the, average across these benchmarks, all levels of the cache. There is more analysis. Sometimes you can save more with L1 for some application, more with L3, static, dynamic energy, and so on. We can talk offline about it if you want. Adapting to problem size. Even with a single application, you need different cache sizes for different problem sizes. So when I took HPC CG, just a good example, and changed the problem size and saw what configurations the approach would use. If you have 10 cube, like 10 by 10 by 10 domain, very tiny domain, it will use only 1 way of L3, this red line over here. As you increase it, it's going to increase the number of ways, as you expect. When this point, it has like, it fits the cache almost. When you go over the cache size, it doesn't matter too much because you are going to have cache misses anyways. If you have a domain going through a domain and you come back and it's not in the cache, then it's not in the cache if the domain doesn't fit the cache. So it uses a smaller fraction of the cache. Looking at the energy savings, when the size is small, we can save a lot. Then we can save less, and here we can't save too much because the application is using the cache properly. This is what is called like energy proportional computing. I spend energy when it's needed, not anymore. And when it's wasting the energy, we can save it. So adapting to the problem size is very important for caches. Another thing, based on the patterns that we saw a lot of streaming. And there had been a lot of work on streaming for HPC applications. So and I'm going to go through what we propose for streaming. So streaming approaches predict the data and prefetch them to hide memory latency for simple memory accesses. However, it's not very easy. Streaming and prefetching is not very easy. You need to know how much cache size you're going to use, the buffer size, cache size, whatever you are using for prefetch, and you also need to know the prefetch depth. How far am I going to go? and bring data before they are accessed. If you go too far, you can waste a lot of energy and memory bandwidth. And going too far, it's going to evict useful data. You're going to bring some data that's not useful and kick out the useful data. You just want to prefetch enough data that will hide memory latency but not waste anything. The runtime system, based similar to what we discussed, can tune the cache size and depth properly. So implementing this in hardware is much easier than other prefetch approaches. So the prefetcher has some address, some adder to generate the next address. If one input is set by the runtime as a system register, it's going to set prefetch deeper addresses. That's it. It doesn't have, so in the compiler approaches, you have prefetch instructions, which have a lot of overhead. Here, we just set a register, not too much overhead. There is some performance energy trade-off here as well. If you prefetch, this graph shows the performance of the application with different prefetch depth on the x-axis, and these lines are different cache sizes that were used. The blue to green shows 8 ways to 16 ways. So the difference is very tiny in terms of performance, but energy-wise, green consumes much more, which is like 16 ways, using 16 ways. So there is a lot of interesting trade-off. But this approach in general can save a lot of energy and improve performance as well. We saw up to like 30% improvements in some cases. However, this is very difficult for hardware to do on its own, and we need the runtime system. This is some good example of showing the complexities. So this graph shows the prefetch depth and miss rate of the last level cache. If you just monitor the miss rate, you want to decrease the miss rate, right? You're going to decrease the miss rate forever in this graph until 128 prefetch depth. However, the performance is not going to improve. This is like a mystery. Why? I'm decreasing the miss rate, but the performance is not improving. It turns out that when you prefetch more, the wrong speculative path is accelerated more. So in modern processors, we have branch prediction. So it speculatively executes some instructions and rolls back if they were, and doesn't commit them if they were wrong, if the branch prediction was wrong. So in this case, with deeper prefetch, this graph shows that for the exact same computation, more instructions are issued for the same computation, which means that those wrong instructions, those wrong paths, were making more progress, and we're not letting the actual computation move forward as much. So prefetching is very tricky. It's not very easy to do. And this automatic tuning, kind of oblivious tuning, is a good approach for doing it. Just looking at the related work, there is a lot of work of doing these kind of reconfigurations in hardware, and there is some survey we can look at, but they didn't find their ways after years of research into actual hardware because of the complexities. So because of hardware complexities, you're going to have energy overheads. It might not be worth it. It's hard to predict the application's behavior in hardware. The window that you're characterizing might be too small. You don't know what configuration is the best in a single processor, and so on. There had been some work on compiler-directed reconfiguration. However, they assume simple affine nested loops, simple array indices, just array variables, constants. They don't. It doesn't seem feasible for real HPC applications. In conclusion, caches consume a lot of power in supercomputers, and we can use the runtime system to predict the application's behavior and change the configuration. We can predict the behavior using formal language theory and building a finite state machine kind of thing, and find the best configuration in parallel because processors are doing same or very similar things. We could save a lot of the cache energy, 67% on average across the board. And also, we saw that streaming can improve performance and save energy, reconfigurable streaming. 30% performance and 75% energy for HPC CG. For future work, some prototype machine at runtime that would actually do this would be very interesting. MIT Angstrom has a project, has a prototype chip that does this cache reconfiguration. We are going to see what will happen with that. And also finding the best configuration in smaller scale when you can't try all the configurations is interesting. We can exploit common patterns and the properties of them to do that. Also, it turns out that it could be extended to some mobile applications, non-HPC small scale, because some new mobile applications have very similar characteristics than HPC. Like you have convolutions through some camera's image and so on, and different iterative steps. So this is the future work, and I would be happy to take questions.
When you were talking about the Stencil computation, you conveniently said that you weren't going to block it because it made the analysis easier. How many of the other results you reported also ignores blocking, and to what extent is proper use of the memory or cache hierarchy taken into account?
Whenever I talk about this, somebody asks for blocking. So with blocking, I didn't test it because none of my benchmarks were doing it. But you don't need to use the whole cache for blocking. I can argue that you can, the whole L3 cache. If you use L2 cache, maybe it's faster, the block size of L2 cache. Recent work has shown that you should tune the block size. It doesn't need to be L3 cache. I didn't explore it because Mantivo benchmarks are not doing it. And I hadn't seen any MPI Fortran large code base doing blocking properly. So if I get a hold of that, I can try it with my simulations. But that's another aspect. It's not an issue for us. If you do blocking for Stencil, what I said was that instead of multiple streams, it's going to be one stream because you can reuse the two other streams. It's not going to change anything. We can discuss offline going through the algorithm, but it's not going to change our approach.
Your table of the optimum cache sizes suggests that the L1 and L2 caches are grossly oversized. So what's driving that?
One thing is that if you have streaming, you have a small loop, let's say HPC application, going through a lot of things, then coming back, like a lot of iterations. You don't need to, so L1I, you don't have too many instructions in that loop, maybe.
The question is not why this is the optimal practice. The question is why are processor manufacturers putting these large caches there?
Yeah, I'm going to get there.
Okay. Yeah.
This is for HPC.
I know, right, yeah.
This is for HPC.
Yeah.
For non-HPC, this is not the optimal. So so this this means that a small loop, a few number of instructions is being repeated. I don't need a lot of instruction cache. And L1D cache, maybe it's not very useful for HPC when you have a larger domain. For commercial things, you have a search or something. When the data size is very small, fits in L1, awesome. Here you don't have it. Yeah, but the thing is, what I'm proposing is that just adding this support to this commercial processor, it's going to fix the HPC problem. This is very minor, like turning off ways, it's very minor supporting hardware. Just like what you were saying with minor support and software approach.
Actually, it's simpler than that. It's that the commercial code bases, either because it's a Java virtual machine, it's a Python runtime, or it's a rather complicated multi-branching code, have very deep call graphs. Mm-hmm. A very deep call graph will fill both of these spaces up very quickly. It's the stack that runs out of these two spaces. Mm-hmm. That's why they're built like that. Mm-hmm. Whereas our HPC, we've already pruned all that crap out, right?
Yeah. Thank you for the comment.
Well, the other way to say it is that this typically test suites are too narrow in their problem domains. And if there are other problem domains.
But even large HPC applications, I don't think they would have big call graphs.
Yeah,
they do.
Good simulations are much more like that.
Borderline between HPC and the rest of the world. Scientific computing.
But those applications, although I'm mainly considering CSE kind of things, not those applications. But I'm guessing for those, you could save much more in the L3 cache than L1 and L2, probably, because you have some events, smaller events. You are not using L3 cache as much, I'm guessing. I should look at the applications you're using. Yeah.
So I have a comment on your observation that IBM does processors for HPC and Cray doesn't. They use general.
No.
Maybe that's a reason for IBM not delivering what they promised.
Yeah.
So,
we have to use commodity. We are a tiny market, right? And even IBM, it's a little bit tweaked. It's like they're all power processors. It's not designed from scratch. You cannot design for HPC. It's multi-billion-dollar investment.
So given that it's so easy to change the ways, would an empirical approach work for other workloads where you cannot model it with the iterative model? I mean, just turn off half the ways, measure, and just do a binary search in the number of ways? I know this is, I'm talking about the future when it's the whole point of simulation is to influence future hardware. So, for these other workloads where your iterative regular language approach may not apply, like a recursive task thing, just an empirical search of the right number of ways might get you there, right?
Yeah. Depends on the application. But you are right. It could get there.
Let's thank Ehsan.
Thank you for your time.